right now in Spain, in Galicia. It is 4 o'clock p.m. here. And today we are global. So it is also, of course, allow me to say that we are connecting with the Washington, D.C., where Optica has headquarters, but also with companies that are all the way from Silicon Valley to Japan. We are truly global today. Ladies and gentlemen, welcome to the online industry meeting, the second of the online industry meeting series of Optica, to our online industry meeting on ultrafast laser applications. Every time somebody mentions ultra-fast lasers, I get very excited, and then I start talking non-stop about great companies like Fluence, Amplitude, Light Conversion, Femtum, Expla, Prospective Instruments, Luxinar, Class 5 Photonics, Optica, Menlo, Valo Innovations. I wish there was time to mention everyone. Even though the physics inside the femtosecond generators are amazing, the next Optica Online industry meetings on Tuesday, 27th of September, will not talk about that, because our focus will be on new applications that are ramping up fast. Let's start with glass processing. Efficient, fast, and affordable glass processing is in big demand today, not only because of the underreported global high-quality glass shortage, but also because here comes the micro-optics revolution. We are seeing micro-optics used everywhere, from jewelry to clothing, from car lighting to silicon photonics transceivers. So in our first online industry meeting on ultra-fast lasers, I want to spotlight the rising stars in micro-optics manufacturing with femtosecond lasers, like FemtoPrint in Switzerland. They 3D print micro-optics with what? With ultra-fast lasers, of course. What do they need? And more importantly, how can we help them accelerate their preferred future? Let's ask their CTO, Andrea Lovera. Next door in Germany, we are planning a visit to Fraunhofer IOF in Jena. They are exploring how a new generation of high-power, ultra-fast lasers will impact renewable energies, batteries, manufacturing of next-generation electronics, as well as medical devices. We'll hear from their Director of Laser Technology, Jens Limpert. From Jena, we go to Barcelona, where we meet one of the companies that have provided major brands with early access to prototypes: perfume bottles, automotive lighting, jewelry, antibacterial surfaces, industrial engraving. I'm talking, of course, about micro-reuse. We will engage with their CEO, Raúl García. And global as we are, it is time to cross the Atlantic and meet one of the figures I admire the most in this laser industry, fellow and CTO of MKS Spectraphysics Lasers, Jim Kafka. We will expand the conversation to include applications such as silicon scribing and cutting, PCB processing, as well as battery and solar cell production. And we save the best for the last, a contribution from Ji Kiao, a recent recipient of the prestigious Fulbright Award to advanced ultra-fast laser material processing technology. Ji will explain how to manufacture photonic integrated circuits using ultra-fast lasers. But exactly, what are the specs for the amazing laser she needs, and using which laser optics and other components? Remember, the date for your diary is Tuesday, 27 September, starting at 7 a.m. in Silicon Valley, 10 a.m. New York City, and 4 p.m. here in the Netherlands. Remember that you need to register to be part of the conversation at this address. And at any point during the meeting, you are welcome to share one slide about what you are doing to advance the ultra-fast laser business. Thank you very much, everyone. Thank you for making a dream come true, because I take this topic very close to my heart. I wasn't acting in the video. This is how excited I get when we talk about ultrafast laser, and especially when we talk about the applications. I would like to thank all the companies, many companies who gave input for this meeting, who told us what applications we should target, what companies we should bring. Thank you very much. We couldn't have made it without you. And also would like to thank all speakers who come here looking for potential partners, looking for potential companies that can help them succeed. So everyone in the room, and we already have 76 people, and I'm sure this number is gonna go up quite a bit. Everyone in the room is welcome to contact each other, to chat with each other. Just make sure that we use the next 2 hours of your time to find potential partners, suppliers, customers, investors, and who knows, maybe even hireable talent. Thank you very much for being with us. My name is Jose Pozo. I'm the Chief Technology Officer of Optica, and I would like to let you know that I joined already 6 months ago with the goal, with the mission, together with my team, to build a global industry networks. And that means to help our members connect with other companies. And what we're doing constantly is to introduce them to other companies. The reason why you join an industry association is you want to interact with the other companies. That's why you're here. We also help you to connect, to find research partners, to find connections with the industry and with investors, and of course, to find the most scarce material of this industry, which is employees. Thank you very much, all of you, for being a corporate member of Optica. We are already 24,000 individual members and 350 corporate members. I would like to say that I'm speaking on behalf of a fantastic team, 160 people staff Optica has, but also on behalf of our Corporate Engagement Council. These are the people who tell us what to do. So if we do anything wrong, if Tom Houskane, Elise Friskage, or myself do anything wrong, please blame them. They are the one who told us this is the way to contact the industry. Of course, that's a joke. Thank you very much, all of you also that will be at the Frontiers in Optics in Rochester. We're preparing something very special for our corporate members there, an end user workshop. Do not miss it if you're going to be in Rochester and you are representing the industry part of Optica. I would like to let you know that we have a really big program of events, a really big program with events. Let's make sure that you register as soon as possible. Today we are talking about new ultra-fast laser applications, but for many of you who are going to be at the 26th, 27th of October, we have a historic event on co-packaged and pluggable optics at DuPont in Silicon Valley, and on the 8th and 9th of November, I just got a confirmation ID Quantic is going to be represented by the CEO in our Quantum Industry Summit at IXBlue. We keep connecting the industry. We keep building a global industry network, but that's enough about Optica. Today is about new ultra-fast laser applications. And you already heard the kind of speakers that we have today, so you already know this. What you don't know is that we also have 200 companies that registered for this meeting and gave input. All these people that are in this slide, all these companies that are in this slide are represented by people who have registered for this meeting looking for potential partners, suppliers, customers, investors, and talent. So if you want to get in touch with any of the participants today, all you have to do is send me an email, jpozo@optica.org, and I will make the introduction. Please let me know why you want to get in touch with them. This is what I really wanted to tell you. 240 companies are here with us today, either in our YouTube channel or here with us live in Zoom. Thank you very much, all of you, for that. And remember, keep following the Optica activities, keep engaging with us, keep interacting with us, because we are here for you, and we are nothing without you. And with that, I would like to start the meeting. And to start the meeting today, we have something very special. We brought one person that means a lot to Optica, that means a lot to the ultra-fast laser business, and that means a lot to our corporate members. I'm talking, of course, about fellow and CTO of MKS Spectrophysics. Thank you very much, all the way from Rochester, Jim Kafka. Thank you very much for being with us. The floor and the attention of everyone is yours.
Why, thank you very much. Not in Rochester, in Silicon Valley now, but I did my decade in Rochester a long time ago, and I have lots of friends there and hope to be there soon. Yes, good morning, good afternoon, good evening, and I'm glad to be with the rest of the panel. Let me show you my slides and tell you a little bit about MKS and spectrophysics. There we go. Okay. So you may know that spectrophysics was purchased by Newport in 2004, and all of us became part of MKS in 2016. And as of this summer, MKS is $4.5 billion company. But spectrophysics, as you know, is the laser part of that whole business. And one of our strategic focuses is investment in ultrafast lasers and going after multiple markets. I'm going to tell you a little bit about some of the markets that we're interested in. A little bit of history. We've been making ultrafast lasers here more than 40 years, going back to dye lasers in the late 70s. I found in my collection a brochure from 24 years ago where we were boasting expand your ultrafast universe. And in the picture were Ti-sapphire oscillators and OPOs, second harmonic generators, pump sources, OPAs, amplifier systems, all that already in 1998. So I'm going to segment the markets that we participate in into 4 different segments here. And I'll tell you a little bit about each of them because they have somewhat different products, although there's some overlap. And they also have somewhat different customers, which means customer needs are different. And then you're going to hear a lot more about a few of these markets from the rest of the esteemed panel. So let me start with scientific research. A typical product for this market might be a Ti-sapphire oscillator, Ti-sapphire amplifier, or an OPA. And customers are physicists, a lot of chemists, people in government labs. And one of the key things they value in this market is flexibility. That is variable rep rate, getting shorter pulses, longer pulses, maybe longer pulses with transform limited bandwidths, getting different wavelengths out of the OPA, and timing and synchronization. So flexibility and performance is really big, but it's a very interesting mix of users. Some of them are very sophisticated and they want to have their hands in the laser and adjust things. Other ones are either first-time users or other researchers who are much more interested in what the particular work they're doing, and they don't want to use their hands in the equipment at all. They value ease of use more highly. And so all of those customers are people we talk to and work with and whose challenges we try and solve. A big market for us is bioimaging. You can see a pretty picture here from a multiphoton microscope and a description of what sort of applications people use them in, such as neuroscience and studying the brain. A typical product here is a very broadly tunable 100 femtosecond source, but with dispersion compensation to compensate all the dispersion that's in the microscope. This is also a bit of a complicated market. Sometimes we sell directly to a researcher and they will have an existing microscope, or they'll decide what microscope they want later, or we actually have to work through the microscope companies. There's a bunch of wonderful ones out there. Sometimes they want to borrow a laser for many months and qualify it with their particular system. So we have to satisfy both the microscope companies' needs and sometimes the direct customers. Number one is probably performance. But in fact, ease of use is very important. They have to keep their microscope going. They have to prepare their samples. They have to do all the science that they want to do. Often they don't want to mess with the laser that much. These are largely lasers with no knobs that you can touch and one computer screen that lets you do the tuning and adjust the dispersion. Going down to the lower left, here's a very pretty picture of a stent as a representative of the medical market. Products in this market, a typical product would be a diode pump system, and it might have fiber as the gain, or it might have bulk crystals, or it could be a hybrid source where it's got fiber and bulk for each of their 2 advantages put together. And typically they're femtosecond pulses, although some of the stents are done with slightly longer pulses. And in this market as well is LASIK or other eye surgery. And in this particular market, customers value reliability and minimum number of adjustments. The surgery customers may not use the laser that many hours during a year. They're not looking for running it all the time, but it has to turn on every single time. So reliability is one of the key hallmarks of the medical market. And then industrial, you're going to hear a whole bunch more from the rest of the panel. Also typically diode pump systems with fiber or bulk or hybrid gain media, and femtosecond and picosecond sources these days. What do customers value? It depends a lot on their applications. Throughput is very important. How fast can I finish my process? Uptime, I don't want to be down at all. I want to have the laser running whenever I need it for many, many hours and every single day. Cost of ownership is important. Do I have to refurbish the laser? And how often do I have to do that? I really want to know how much money I'm going to spend every year doing my process. Sometimes customers run the lasers 24/7, that is every hour, all day long. Beam quality is very important, but so is the support we give people in applications labs. they need to optimize their process. And we often get questions like, is it better for picosecond or femtosecond? Does it make a difference? Do I want IR? Do I want green? Do I want UV? How about burst mode? Can I make my process go faster if I rearrange the pulses in time? Some customers, a lot of them, actually want integration support, and they value that. In fact, at Newport, we know all about power meters and tables, and particularly optics and damage and lifetime of optics. So I've tried to summarize what I said about the 4 different markets that I segmented for you. What do customers want? Different customers want different things. Some really want high throughput so they can get the process done quickly. Some want flexibility, that is different wavelengths, dispersion control, etc. Some really need cutting edge performance. You're not going to get your optics letter published if you haven't done something that's at least better than somebody's done before. They want repeatable performance. If a customer is going to buy 100 lasers, they want to know they're all going to be the same and that they don't have to test all of them when they come in. And many customers don't want to mess with the lasers. They want ease of use. So in order to satisfy this, we have a wide range of skills and technologies we need to be experts at. Diode pumping of fibers and gain media, mode locking methods, of course, how to build the best amplifiers with the best beam quality and the best performance, what sort of software and graphical user interfaces, and what kind of electronics. In many of the systems, you need to have AOs and EOs and know how to run them efficiently. And of course, for all the harmonics and for all the optical parametric devices, we need to be nonlinear optics experts. What do I want from all of you on the call? Well, as mentioned, we're always doing workforce development. That means we need skilled people. We want people who have hands-on and lab experience, know about designing lasers, and know about all the technologies I just gave you. And of course, we're always excited about new challenges and new markets and those sort of things. So we do want to hear from you. Thanks for your attention, and I look forward to seeing what questions we get later.
Thank you very much, Jim, for this introduction. You did a fantastic job. You put the meeting in the way that it should be. It is great to have a great group of people with us who, this is not a webinar, Jim. These people are not here to ask you very difficult questions. These people are here to help you and to find ways that we can all work together. A new concept in the industry. We have very different companies in the room, companies that provide different kind of optical elements. And I love because they know what I'm going to do here. So they are prepared, all of them, that they know that eventually I'm going to come to them. For example, I just see that there is a company from Switzerland in the room that they manufacture micro-optics and optical elements. I'm talking, of course, about a company called Axetris. Thank you very much, Muxin, for joining the call today. I would like to ask you, what does Axetris do, and what kind of value can you bring to ultrafast laser manufacturers and system integrators in this industry? And let's see there is a match for cooperation.
Thank you, Jose. Hello, everyone. So I'm Myunshik from Axetris, and we're manufacturing for micro-optics and including micro lenses and diffractive optical elements. So our micro-optics are used a lot in telecommunication industry, but those are, for example, coupling and collimating lenses for the transceivers. But in fact, our micro-optics can do laser beam shapings, like cylindrical lens arrays for line generators, or beam homogenizers, or diffractive optical elements for spot generators. So today I just want to look for the laser applications where our micro-optics beam shaping can be applied. And then I'm sorry I joined a little bit later, so maybe I cannot do further follow from the previous presenters. But that's all I want to say today. I want to be short like that. So if you have any inquiries about laser beam shaping or optical elements, maybe you can talk about later.
Thank you very much, Mixun. And we have many, but I would like to direct the question back to Jim. Jim, could you tell us about the needs for beam shaping and the micro-optics, not the regular optics, the micro-optics that you think could bring value to the beam shaping in ultrafast lasers?
So I'm probably not the right person to answer all of the micro-optics and telecom sort of applications. Our needs certainly are delivering high power beams to samples. So things like making bezel beams or making flat top beams, some of the more macro optical beam shaping things are things that we're interested in. In many cases, our customers make those choices directly and don't necessarily come to us, but we do run applications labs, big one in Silicon Valley, but one in Korea and one in Japan and one in several other locations as well as in Europe. And in each of those, our customers will come to us and they will ask us questions about beams. So again, the area of our interest would be more in macro beam manipulations. I think hopefully the other panelists will know more about the more micro beam applications that you're our expert at.
Thank you very much, Jim. And I can tell you that Axetris provides micro-optics for datacom telecom. They do a great job, but also they do micro-optics for laser beam shaping. But we're going to address this later, because now, Jim, I want to introduce you to another corporate member of Optica and a very good friend of mine. I'm going to go all the way from Switzerland to Greece to meet Andreas Theodosiou from Lumoscribe. Andreas, hello, how are you today?
Hi, Jose. Good. Very nice to see you all.
Andreas, I am a very, very curious person. First, I would like you to tell us very quickly what you do. And second, I know you came to this meeting looking for a certain ultrafast laser. So you could tell us a bit of the specs that of this laser that is in your Santa Claus Christmas list.
Yeah. So Lumoscribe is basically working with optical fiber sensors and fiber lasers, and more particularly for mid-IR lasers. And in Zeblan and indium fluoride, this kind of fiber. So we really need femtosecond lasers for this kind of inscriptions. So not sure if I answered your questions, but yeah.
You shared, your colleagues shared with me the specifications privately, so I have them. If anyone is interested, please contact me. But I would like to direct the question to Jim Kafka. Is there any particular set of ultrafast lasers that you would provide, that you would propose, that you would recommend to Lumoscribe for this particular application?
I think I would want to know more about what you've read in the literature and what sort of wavelengths you have experience with. I know less about the Zeblan materials and inscription. Is it mostly done in the near IR with femtosecond pulses, or are there other wavelengths that help your process?
Usually we work in green, in second harmonic, but I believe that in higher wavelength, the inscription will be more efficient, less lossy, let's say like that. But yeah.
The bulk of what we make are either IR, green, or UV, and again with all the different pulse widths, it sounds to me like it's the sort of thing where you want to get your samples in front of a few lasers, because actually choosing the wavelength is one of the first things you need to do, and choose the pulse width that optimizes the process. So I don't think I can propose an answer, but I can at least propose that A, we can look at the literature together and see what other smart people have already done, and B, if you have materials that you think aren't completely optimized in terms of the process, the next step is to figure out femto or pico, and also whether green is really the best choice, or whether you can get either higher quality or higher throughput. I think in your case, throughput may not be as important. You're not doing enormous amounts of material. I would think having higher quality would be the more important thing. So I think it's a job for the applications lab after we read what other people have already published and told us.
Yeah, that sounds good. Thank you.
Thank you very much, Andreas. Jim, let's talk about pulse width. Of course, not very often, the shorter the pulse, the better. But I'm seeing more and more applications in the 100 to 200 femtosecond pulse regime. What, in your opinion, in the ultra short pulses on the 100 femtosecond pulses, what are the killer applications?
Well, maybe I will answer the question a little to the side. It wasn't exactly as you asked it, but one question is, why would you even want a picosecond laser if you could have a femtosecond laser, and is shorter always better? And I'm hoping the rest of the panel is going to jump in and help me with their version of the answers. In many cases, picoseconds can do the job very well, and actually the systems tend to have more power and cost less money. And so when I talked about throughput at the beginning, you don't want to buy something you don't need. You don't want to pay extra for something if you don't have an advantage. And you want the cheapest system that will do the job well enough for you. And as I said, there's a large range of distant customers who have large ranges of different materials. And as we like to say, one size fits one, not one size fits all. So in fact, that's why there's applications labs and support, because people want to have the highest throughput for the lowest number of dollars. So there's times when picoseconds win. There's other problems with going to very short pulses. There's wonderful stuff in the literature that people have done using much less than 100 femtoseconds, but then you have to worry about dispersion in your optical system and the mirrors that you're going to use and other complexities. And the same with wavelengths. There's some lovely things to do with 266, but keeping the systems happy, keeping the optics clean, not having damage can be a problem. So there's always a balance between how much complexity you add for getting either shorter wavelength or shorter pulses. And again, one size does not fit all.
There are two companies that I want to introduce you. One is from Lithuania, another one is from Poland. And people who know me, they know that I have a weakness for Poland. It's my favorite country in the world. But I'm going to go first to Lithuania, because you mentioned not to damage the optics, Jim, just now, because I was listening carefully. Is there an unmet need when it comes to optics with very high laser-induced damage threshold?
Absolutely. And one of my pet peeves, and you're going to introduce me to the gentleman from Optiman, and I believe we've met in Zoom, but not in person before. And they do great stuff. You should know we also make a lot of our own optics for the same reason, but we're always out there talking to other suppliers to see what they can supply that we actually need. One problem is often customers don't fully appreciate how important the optics are and exactly what damage threshold you need. And then my one little pet peeve is that often what's not important is 10-shot damage threshold, but thousands of hours of lifetime. And it's very easy to measure 10-shot damage threshold. It's much harder to quantify long lifetime. And so that's one of the things where we've gravitated to a simple quantifiable measurement that isn't exactly one-to-one mapping with what quality and what customers need. So I would say that in addition to a need for really good coatings and lovely IBS sort of coatings that they make in Optiman, there's also a need for some better metrology and better testing. And in fact, cleanliness can completely wipe out how good your coating is. You can have the best coating in the world, and if you don't have the environment right, you're not going to get good results. So there's an entire integration, education, and optimization that has to take place for the end customer to be happy.
Jim, following that recommendation, we are going to have a workshop on LIDT measurement, and I'm going to, of course, invite Lidaris and Highlights to be with us. But yes, Jim, you read my mind. I'm going to introduce you to my friend Konstantinas from Optoman, because Konstantinas, you have joined, I think, all the discussions that I had on ultrafast lasers, all of them. What kind of recommendation do you give to the companies who are bringing femtosecond lasers to different applications?
Well, first off, thank you for such a nice introduction. And I couldn't say better than Jim, because Jim made the perfect points about the cleanliness. You need to meet in your lab, and of course, about the ultrafast lasers, many applications, but the laser is as strong as its weakest link, and sometimes it's optics. Yeah.
I have the recommendation to say that, of course, many of our corporate members are providing IBS coating for optics. Please always contact Optica when you're looking for a particular optical element for beam shaping. I have a fantastic team of experts, and we can help you connect with the right corporate member that can help you. That's what we do for a living. We organize meetings for fun, but the real thing we do for a living is connection. Jim, stay with us, because I'm going to come back to you, but I would like to say it has been an honor just being on the same stage with you. Thank you so much.
Can I ask Jim one question?
Of course.
Jim, there's like a trending topic, multipass cells. Is spectrophysics developing this technology to your systems?
So I can't tell you anything about what we don't sell today. I will tell you that I think we did the second experiment ever and didn't actually go back and publish it. So it's an area where we have some expertise, but we don't currently sell anything in that area.
Okay, great.
And like you, I love going to Clio and Advanced Solid State Laser, put in my plug for my favorite Optica conferences, and seeing what everyone else is doing. It saves us a lot of time to have the rest of the world developing things.
Clio is fantastic, but frontiers in optics is Amazing. That's my favorite conference worldwide. Jim, please stay with us. I'm going to come back to you. Jim is in Silicon Valley, who is really in Rochester, is Ji Kiao, our second speaker today. We want to talk about medical imaging, and that's why we're going to the Carlson Center to ask Ji which lasers she needs, which optics she needs, and then having companies in the room, like, for example, Fluence, help them solve their challenges. Thank you very much, Ji, for being with us today. The floor and the attention of a lot of people already in the room goes to Rochester, goes to you.
Thank you for the introduction. Hello, everyone. It's good to be here to share some of our experience and need for ultrafast lasers. So I'm going to share my screen. Oops. Are you seeing the right screen?
Crystal clear.
Okay, so just a little bit about myself and my group at the Carlson Center for Imaging Science at Rochester Institute of Technology. So I lead a group. We focus on using ultrafast lasers to make optical components and photonic devices. So that includes using laser to polish optical surfaces, to figure different form, and using laser to make active and passive optical components. Also use laser to connect optics, crystals, or metals for micro optics integration. And along this, it's also important to understand the physical mechanisms of laser-metal interaction. So we build advanced ultrafast imaging to understand the time scale and physical mechanisms of the laser-material interaction. So Jim gave a very good overview about different types of lasers and application in scientific field and also in industry. And this is my favorite projection for ultrafast lasers. So ultrafast lasers, based on the presentation from Eric Motet from Amplitude, it shows the growth of laser power from 2001 to 2021, going from 1 watt to 1 kilowatt. It grows exactly with Moore's law on power scaling. So the application and future growth are unlimited. We are actually using femtosecond laser to make lasers. The two figures on the right you are seeing are inscribed by femtosecond laser. You can just use a 5 watt laser to do this work. And that actually gave you lasing on a chip level. In this particular one, is lasing at 1064 nanometer, but we were able to do frequency conversion to convert that to mid-IR or visible wavelength. That have broad application in life science or chemical sensing. So I'd like to introduce a few emerging applications using ultrafast lasers. The one on the left I'm showing is called optical far field induced breakdown through enhanced near field enhancement. So the principle is that the focused ultrafast laser beam can induce a little hole. But this hole can actually further induce enhanced near field enhancement that allows to write nano gap that has a spatial resolution of 20 nanometer. By controlling the polarization, one can control the direction and radius of those nanolines. So you can imagine you can make different structures, diffraction gratings or ring resonators. This has a very broad application in solar cells or photonic integration. And the one on the right shows a controllable ultrafast laser figuring that produce optical quality surface. With using femtosecond laser to do raster scanning, sub-nanometer surface roughness has been achieved. When you increase the energy deposition or the number of area scans, the material has been removed with a nanometer precision, and the surface roughness has maintained under 1 nanometer surface roughness. And this is a demonstration showing that with the increasing number of passes, a full-step staircase has been created. This paves the way for creating free-form optics using ultrafast lasers. And the one I want to, next one I want to highlight is produced by a emerging new type of laser called gigahertz laser. This is the holes drilled with gigahertz laser. The difference, you can see that with the increased number of bursts from 100 to 1,000, the hole of the depth of the hole has increased from about 70 micron to 300 micron, with a very uniform inlets and outlets. This has really good application for optical interconnect, like interposer. For photonic integration or optical communication, one of the bottleneck is to connect fibers that has a core size of a few micron to 10 micron to silicon-based photonic devices that has a core size like 1 micron. So ultrafast laser have been used to make those tapered wires to connect the waveguides with the multi-core fibers. So that's for photonic integration. And another very useful application is to use ultrafast laser to manipulate the optical property of glass. In this particular case, by texturing those sub-micron nanopillars, one can produce a surface that has enhanced transmission, or we can create anti-reflection, anti-glare, or anti-fogging. And this, you can imagine, has a broad application in aviation or solar cell industry. From metal processing point of view, it has been commonly used using ultrafast laser to do marking or coloration, or anti-water. These are the creation from different laser companies. So I want to just show a few examples, but the point here is that from end user's point of view, if you look at the trajectory, the laser are going to 1 kilowatts or 10 kilowatts. But what do we need? I think the urgent need is really fiber-guided, flexible, and robust beam delivery system. And the second one is that it is rather important to understand the physical mechanisms of laser material interaction because many interactions are material dependent. But however, it's also difficult to model different individual intelligence enabled processing, I think, is on the horizon. And it will be very powerful when it's integrated with robotics. And the last one, I echo what Jim has said, that what we need is workforce. What we need to train next generation photonics or optical engineers. We need to have co-design and co-creation for ultrafast lasers and laser-based applications, because the industry usually, when they develop something, they have a little bit near timeline, like 1 year. At university, we have about 3-year timeline to train a PhD student. So we are actually indeed need to learn the process, how to create this ecosystem combined with industry, government, academic force, utilizing our own unique strength. Actually, I'm actually glad to share that Rochester is making an endeavor to create such an engine to promote the interaction between those entities for ultrafast lasers and laser applications. So that's all I want to share for now. Thank you.
Thank you. You know, after a presentation like that, and there are people who still say thank you to us. Thank you very much for being with us today. We have a lot of questions and comments, and mostly we have a lot of people, a lot of people who are here because they want to work with you. So I'm going to ask you something out of the blue that maybe you were not asked before, which is that there are 200 people registered for this meeting that will develop lasers, optics, specialty fibers. What can they do for you? Do you have a couple of challenges, unmet needs, a special laser that you would like to have and you couldn't find?
I like to have a fiber delivered beam for my laser, as I mentioned. Right now, it's all in free space. I also like to have flexibility in terms of what type of beam shaping. I think there was a gentleman who mentioned beam shaping. So right now, the beam shaping is cumbersome. People use basal beam, they use spatial light modulator, but they actually, it's rather difficult to switch between a Gaussian beam and those shaped beam. I think a versatile structure that allow us to switch between different type of beam shape, that would be very useful.
We're going to find you the beam shaping, and I promise I'm going to find you the fiber before the end of this meeting. That's my challenge. But before that, there is a couple of people I want you to meet. The first one is one of the companies in Optica that manufactures lasers that go from nanosecond to picosecond. I'm talking about Photonic Industries International. Thank you very much for being with us today. Joyce.
Yes, thank you, Jose. Jay, I was just curious, what type of ultrafast laser did you use for the laser polishing, I guess, pulse width, the wavelength, etc.?
So the ultrafast laser I use for laser polishing is a femtosecond laser. You can buy this type of laser from Amplitude or Coherent.
Do you know the exact pulse width?
The pulse width is around 300 femtosecond.
Okay. And what wavelength do you find good for your laser polishing?
So depends on the material. So we have successfully polished semiconductor material, germanium, and also glass material. And we use 1030 nanometer.
Oh, so fundamental?
Yes.
So you didn't need to use harmonic?
We didn't need to use the harmonic. That's correct.
I see. Okay.
But in terms of waveguide writing, like waveguide laser writing, we were able to write waveguides inside crystal with both IR and the second harmonic.
I see.
You're gonna love the presentation from Andrea Lovera from FemtoPrint later, so please stay with us. But I have another person, G, that I would like you to meet. You talked just now about the 300 femtosecond laser from Amplitude. Do you see applications on the 100, 150 femtosecond pulse lasers, G?
I think the application for 100, 150 seconds, there are more application for life science. For laser machining, I haven't seen a big difference between using 300 femtosecond versus 150 femtosecond. It's mainly because of time scale of the plasma generation or thermal effect.
this is when the meeting gets cool, G, because I'm going to introduce you to one company that has been a success story for the ultra-fast laser ecosystem already for a few years, which I met them on the first months of development, and I have seen them grow, and I have been amazed by them. I'm going to go to Warsaw to meet Dariusz Wierat from Fluence. Dariusz, what are the killer applications on 150 femtosecond lasers? And also tell us, what does Fluence do?
Thank you very much, Jose. Thank you very much, G, for a very nice presentation. I have to say that, well, Fluence, at Fluence, we produce femtosecond lasers based on fiber design. We do not go as low in pulse duration as 100 femtoseconds, but still, we produce fiber lasers that have, I believe, well, one of the best time durations available on the market. So you can go, we can go down to pretty much 250 femtoseconds. And this is something special for us. And well, we have also our application lab. And I can tell you, G, that what we already observed that, yes, for most of applications, 300, 500 femtoseconds is perfectly enough. Even longer pulse durations are actually optimal. But there are applications where 250 femtoseconds, for example, it's really giving some benefit, right? So I can like just show you. So this is our Jasper series. It's well, it's not as high average powers, like you said, not kilowatts, it's 60 watts, it's 100 microjoules. But what we believe at Fluence is that it's really, there's a great potential in femtosecond lasers that is still not used, right? So many people, they look into high powers, high average powers, high energies. But the thing is that by using the right spatial modulation, that's what you mentioned, or also temporal modulation, shaping of the beam, you can obtain fantastic results. And this is something that we also observed in our application lab. For example, cutting of polycarbonate with just a galvo scanner and our femtosecond laser, where we were able to obtain 0.5 meter per second speed. So I believe this is something well, worth sharing. If you would like to know more, just don't hesitate to get in touch with us.
Thank you.
Thank you very much.
Yeah.
Conquest, just tell us, comment please.
So your laser is also fiber laser, fiber-based laser?
Yes, it is. It is fiber laser, and we maximize the use of fiber.
You maximize the use of...
Meaning that the whole construction is fiber, and the only free space component that we have is the compressor at the very end of the fiber.
I see. Okay. I think so. I think there could be some difference in terms of optical, in terms of contrast, the effect on the material processing, and that hasn't been studied very thoroughly. Do you have a measurement on that, or usually?
You mean like what kind of contrast do you mean?
Contrast is the usually fiber laser has a pedestal, and that can affect processing in terms of whether the processing is clean or not clean.
Yeah, absolutely. So yes, so it does affect. And I can also tell you, so I can share my slide. If it's all right, Jose, to share one more slide.
Of course, this is your meeting. I do this meeting for you, not for me.
Okay, so I can tell you, like, I mean, you're right that free space lasers, they are very well developed and they have very good parameters when it comes to, for example, very good contrast, low pedestal. So this is like example of our measurement that we have in our Jasper laser. But I also will make a comment that it's not only what you can see at the pedestal, it is also what you can see further away. So in the post-pulse and pre-pulse contrast, which is like this. So this is picosecond scale. If you look in nanosecond scale, you can find this other artifacts that may hit your sample, for example, right? And also in our construction, we have this record high contrast when it comes to pre-pulse and post-pulse. So it's like 1/5000, and not what is usual in this field, which is 1/100 for the post-pulse. And this is thanks to the design of the oscillator that we have.
Oh, thank you. Thank you for sharing that.
You're welcome.
That's helpful.
Thank you very much, Darius. Dziękuję bardzo, Darius. G, one more thing. When it comes to non-linear crystal, no, wait, somebody just interrupted me because they have a question from Darius. This is not a webinar, this is a meeting. So you have a question, please, Hamid Reza from Ensemble 3 Optica member, unmute your microphone and ask the question yourself.
Okay, hello everybody. Just I have a question from Darius. What about the tunability of your lasers? How much cover you can wavelengths cover that you have from your lasers?
You mean tunability of the wavelength, right?
Yes.
So our fiber lasers, they come with the advantage of higher stability per their lifetime, but on the other hand, because you have the stability, you also do not have the tunable components, right? This is something we had to scrap to get this extra stability, which means that we have fixed frequency laser, so 1030. Then we generate harmonics of green, UV, deep UV. And if you need tunability of the wavelength, then the laser that I just shown, Jasper, it can be combined, for example, with OPA, and then we can provide a solution that tunes from really deep UV up to even 10 micron, right? So this is possible, and this is what the optical parametric amplifier is used for.
Hamid, you are muted. We cannot hear you, and we really want to.
Sorry. And you're making OPO as well?
Yes, OPA. So we do our OPA. Yes, those are based on free space, not fibers, unfortunately. But yes, we do OPAs. If you have any interest, we can chat about that.
Okay.
You definitely should. Back to G. I want to go back to G because I want to ask you, when it comes to non-linear crystals, is there any need, any unmet need? What kind of non-linear crystal do you use currently?
You are saying for making waveguide lasers, or so for making waveguide lasers, we use medium YAG laser crystal. We use lithium niobate. These are the typical crystals we use. I think the medium YAG and chromium. So the crystal we are using are not so exotic for waveguide laser application. But for if you want to go to mid-IR, then it's a different story. I think we do face liking of crystals readily available, different type of crystals.
You know, anytime that you're looking for nonlinear crystal, please contact Optica. We know everyone. We can provide you with the right crystal. That's what we do. But I want to introduce to somebody else because I also love when centers that have synergies contribute and collaborate. There is a center in France called LP3 from CNRS, and I have Alexandros with us. Alexandros, you were prepared for this. Most likely this is not an online webinar, this is a meeting. Could you tell us quickly what you do with tie sapphire lasers and what kind of applications you're targeting at LP3? Alexandros, you are muted, we cannot hear you. I think he's not able to switch on the microphone. He's not able to switch on the microphone, and that's okay. And we understand and we respect. Thank you very much for being with us. I'm going to come to you later and we're going to record it and make a video for everyone to know what you do. But we continue with the program. I want to go to the next speaker now. And that speaker really means a lot to me and means a lot to the femtosecond laser community that I've been a part of for many years. I'm talking about a company in Barcelona that has been providing services for femto and pico-second laser-based surface structuring and other manufacturing. I'm talking about microrelieves, and I'm talking about my friend, Raúl García. Buenas tardes. Thank you very much for being with us. We really want to know what you do, and we want to know who we can use it. The floor and the attention of the Optica community for the first time of many for microrelieves goes to you.
Hello, Jose. Hello, everybody. Thank you very much for your nice introduction. Can you see my screen?
Loud and clear and crystal clear.
Okay, thank you so much. Well, nice to see you here. Nice to see you, all of you. So I will speak today about from the final perspective point of view. So final user, that's what we do. We use the femtosecond lasers to work for our customers in the industry. So what I'm going to speak about is about the femtosecond laser engraving, microstructuring, and texturing for different applications. So we are a services provider for industry. We are a workshop based in Barcelona, and what we do is to give this service using different technologies, but especially femtosecond laser in 5 axes since 2016. So what we do, we work for a lot of different customers, for the packaging industry, medical industry, lighting, automotive industry, etc. So all of our customers have different needs. So I will show here some examples about the projects that we are doing. Some examples in design with functional purpose, for example, thanks to the capacity and the capabilities of the femtosecond laser on how can we work on the tool or on the final part. So we can engrave on the tool or in the mold such as small microstructures to have some holograms, some different images just on how you see the part. That could be very interesting from the point of view of design, but also for anti-counterfeit. So we can see here an example, and we can see that we can see the face of a woman or the face of a man just on how we rotate that. But we engrave the tool, so the plastic injection mold, the plastic is getting inside the tool, and thanks to this microstructuring in the tool, we can see the final part with these characteristics. And the same happens when we are trying to find some colors in the final part, so light diffraction effect, also very interesting for design and anti-counterfeit. Here we can see the final injected plastic part in the tool, in the mold, and we can see the colors as well, just by the replication of the plastic in the engraved tool. Or some other example in the plastic industry is to make a plastic feel very, very soft, very nice, like a velvet effect just of the engraving in the tool using femtosecond laser in this case. Always also over flat or 3D shape. So what we are is the end users of an integration of the femtosecond laser in a 5-axis machine. Another example, this one is totally functional, is hydrophobicity. So we can engrave such this kind of micro peaks in the range of 20 microns to change the behavior of the water drop and put a plastic which is already hydrophobic into super hydrophobic. So the behavior of a water drop when it goes to the plastic injected part is the one that we can see here. So the water drop is getting outside the area which is texturized and is keeping in the area which is not, just because of the topography, just because of the engraving that we can do on this tool. Some other examples, for example, for the lighting industry, light diffusion, which is It's very typical now. So to avoid the hot spot of the LED, to have a surface illuminated, but you don't want to see the hot spot of the LED that are placed behind this part. You want everything to be homogeneous. So with the femtosecond laser, we can create some texture in the tool that makes the plastic to have a homogeneous and controlled diffusion. So there is no need to have all the diffusion in all the part, like this is what happens if you inject a diffuser material, but you can have the diffusion just in the areas that you want and with the intensity and characteristics that you want. That's why we have some developments in terms of texturing to have better luminance or to have better homogeneity. And following the lighting industry, but in this case more focused on the automotive lighting industry, here we can see some examples in the market that we have done using this technology. So in the Range Rover Sport 2023, it was presented recently, around 1 month ago. That's why we can show these images. So we engraved all the micro optics on the production tools for the tail lamp of this car. So thanks to the micro optics engraved here, we can obtain such a beautiful finishing with this homogeneity. On the other hand, on the Cupra Tabascan concept, the idea here is to have a light curtain effect. So here we engraved thousands of microprisms that makes the light to be homogeneous, but in this case coming from the top, not like the previous page that the light was coming from the bottom. And to finish in this Seat Leon 2020 model, the signal mirror indicator to obtain this nice and beautiful effect here in the signal mirror indicator was engraved also in the tool for this purpose. So as a final users for a lot of different applications in the industry, what we found is that the characteristics of this technology that make it very interesting and important for us is that we can obtain in a tool, we can engrave a mold in a way that was not possible before using conventional technologies like milling machine, die sinking, EDM, etc. That of course you are limited of the wear and tear of the tool, limited on the radius of the tool, etc., etc. So with the femtosecond laser, we can engrave microstructures in the size of dozens of microns with a clean, sharp, and burr-free micromilling, very high quality surface finishing with extremely good tolerances, and we can engrave almost on any material. On the other hand, what we feel using this technology compared with conventional technology is that it is very expensive technology in comparison. Of course, we can engrave in a way that was not possible before, that's clear, but with a very expensive price. In addition, when engraving, if we want to reach an excellent quality, the engraving time is very long, so that makes the process expensive. So that's everything I wanted to show and to explain. And if you have any doubt or want to comment something, thank you so much.
There are many things, many things that we want to comment. And also let me remind everyone that the floor is of course open for questions, suggestions, and room for cooperation. But there is many things I want to comment. The first one, I want you to be introduced to a person that represents a European OSAT on manufacturing photonic package devices. Erwin Verheest from Fix BB. Thank you very much for being with us today.
Hello, Jose. Thank you very much for the introduction. Yeah, we do packaging of mainly PICs, photonic assembly of these devices. And yeah, I'm very interested to see what lasers can contribute to that. We saw already some nice photonic wire bonds. And here some wonderful machining that could be nicely utilized for molds for optical components. Yeah, I'm not sure what else I can add here.
Don't worry, because I know what I'm doing.
You go to
trust
make a
me.
link?
When I give you the floor, it's because I have something in mind. Raul, wait, because Erwin is providing packaging services for integrated photonics. And to package integrated photonics, he needs to put the integrated photonic chip, and then he needs to put micro optics that, as Jim very well said before, sometimes they come from a Swiss manufacturer called Axetris. Music, I want to bring you back to the discussion. And I want to go back to Raul. Raul, in the past, we have been discussing quite a lot about the kind of things that the optics community could do for you. And very often we came up with the need for molds, masters for the manufacturing of optics and micro-optics elements. Music. Sorry to bring you to the discussion to this point, but I would like to know, what are the unmet needs, the final frontiers when it comes to masters molds with high resolution for the manufacturing of micro-optics?
So maybe I cannot give a big insight about the mold, because in fact we do micro-optics manufacturing based on wafer. But in fact, we have as well a diversification program for the nano imprint, which is like a replication process. So in fact, we will need a supplier for the mold. So probably maybe some engineering colleague could contact Raul. But at this moment, I think from our side, giving our insight or requirements to the mold is a little bit far.
Music, this is the beauty of these meetings, because the entire supply chain is back. So we go one step higher in the supply chain. We go to femtoprint. Andrea Lovera, can you tell us what, I know that one of the applications that you are targeting, and we're going to see your presentation later, this is a bit of a preview, is the supplying of masters for the nanoimprint lithography and for the companies who are manufacturing micro-optics based on replication. Can you tell us a bit about what are the needs, the challenges, the final frontier in terms of resolution or critical dimension when it comes to the manufacturing of these masters?
So absolutely. So today, at least our main challenge is the metrology. One thing is to produce very good master. The other thing is to be able to characterize them properly. And I guess one of the things that we look constantly is way to do the characterization, because when it comes to micro optics, you need resolution below 1 micron, and that's really challenging to achieve.
Resolution below 1 micron. What is the typical size of the masters that you normally need for this?
So we produce master typically at die level, so a few centimeters square, but we are equipped to make also up to 8-inch wafers. But yeah, that's a different complexity. So today we are really focused on a couple of centimeters squares.
Very good. We're going to hear more about the presentation later, but I want to make a call for everyone in the room here. This is a supply chain. My idea is that I want one company to make the master, supply it to another company who made the micro-optics, supplying those micro-optics to a company like Fix that will integrate them and will maybe package the devices of a company like, well, I have many in the room. A company like Siena, I could say, here in the room, represented by Jean-Philippe Berube. Thank you very much for being today with us, Jean-Philippe. Raul, I know that you already have your supplier for the laser, and feel free to mention it, and they are a really great manufacturer from the laser. A couple of times I've been asking you this question. I will ask you again. When it comes to metrology, when it comes to beam shaping, when it comes to what kind of things can the Optica community do for you to help you be even more successful than you already are?
Well, for us, maybe it's more, maybe we're a strange company here a little bit, because what we do is we do the service. So we are buying the machines, but the machines integrate in 5 axes the lasers. So in terms of the capacity or what is happening inside the laser, we can't control anything, because of course we are in the hands of our supplier of the machine in terms of a guarantee and so on. So we can't ask specific stuff in terms of laser, but in terms of integration, I know that there are a lot of lasers that are not integrated or are not possible to integrate them in a 5-axis machine, for example, or for big parts, for heavy parts, etc. And that's what we ask a solution in the market for big, heavy tools in 5 axis. And as I said in the previous presentation, to be more economic, of course, that's my request as a lot of people, I suppose, because compared with other technologies are very expensive. So that's our needs right now.
Thank you very much, Raúl García. Jean-Philippe Berube from Siena. What brings you to a meeting on ultrafast lasers?
Yes, there are many applications we might need to do with our PIC, for instance, or packages. But just to pick one, I would say that one thing that interests us is laser cleaning of parts. So maybe I think Raúl could. I don't know if your company has done that already, or have you tried? I also noticed G from G's talk earlier that they were doing laser polishing, so I expect that it would be applied to cleaning also. So that's more of an open question, I would say.
Well, from our side, what we have done a lot is removing selectively some specific coating on a part. For example, for lighting part, if the part is transparent and there is some coating, some paint over it, and you want to remove it selectively with micro geometries or whatever, we have done that a lot. Or in terms of finishing, of course, we can engrave our microstructures and leave it like very, very smooth. It's not like polished, but quite close. But I think that your question is more related in terms of milling a part, no, or having a part, and what you want to do is to increase the finishing or to remove the micro grain or micro roughness, something like that, right?
Mm-hmm. Yeah,
the point is that us, we are very dependent on the previous surface. So if the previous surface has a lot of roughness, it will be difficult for us to increase this finishing. I don't know if it's the same case on the other companies, but that's our experience here.
I can add a little bit.
Yes, please.
With the cleaning aspect, so we have been able to clean up the germanium surface we were polishing. Mm-hmm. So prior to the laser polishing, we can see clear scratches and decoloration. After the laser polishing, these traces are gone. And this is one thing. The second thing is that we were also able to see that if there's any debris on the surface, through this laser processing process, we were able to remove them. So the question I have for you is that what type of surface are you looking to clean? Is it glass or metal? And how good is the surface condition?
Yes, usually that's a good question, because there could be many things we would like to, let's say, clean. Most of them, let's say, let's focus on our core. So what those most likely like to clean is silicon part or wafers, dyes that being processed. So there's many things on these dyes. There's a silicon substrate, but there's passivations and metallization on top of that. So it's a complicated things to try to remove particle from such involved material. There's many materials on there, so it's difficult to be really accurate about that. But mostly, we'll say that's mostly on silicon substrate. That's what we will aim for. But yeah, well.
Optica World Network, the challenge is on the table. You have a process suitable for wafer scale cleaning, silicon wafer cleaning. We are looking forward to find out what you do and make the right introduction. Jean-Philippe, thank you very much for that. Yeah. Raúl García, if you start a project with Siena, I would cry of happiness. Thank you very much, Raúl, for being with us.
Thank you, Jorge.
There is a question in the YouTube channel, because I would like to remind this live stream is in YouTube at the same time. So hello, YouTubers of the world. If you have any question, please write in the chat. There is a question in the YouTube, and it's from Raúl Siqueira, who is joining all the way from Brazil, from the Institute for Advanced Studies. And the question is for both Fluence as well as G from Rochester Institute of Technology. I will ask each of you separately. The question is about laser shock pinning. Let me just find it. Are your lasers suitable for laser shock pinning? Is the energy high enough? First, Fluence.
Can you say again? Is it
are your lasers suitable for laser shock pinning?
Pinning. Can you write it on the chat? Pinning,
yeah.
like.
Of course I can. But let me come back to yes.
Okay, so I would say we didn't try this application for sure, but this is why we also have this application lab. So where we love to try any new things that we haven't tried so far. So if you're wondering about whether our laser is good for this application, please get in touch with us, and you can send us some samples and we can check it together. And I will give this topic to Jeet, because I'm also interested if
I would like to give it to G and then to Jim Kafka. G, are you active in the application of laser shock pinning, adding stress to materials, and what kind of lasers are ideal for that?
So my group, we don't do laser shock pinning. So in terms of the type of lasers that can be used for this, I have seen a lot of presentations. They use nanosecond laser for this purpose.
Disc laser typically. Jim, thank you very much for being with us. I told you I was going to come to you. Are you familiar with laser shock pinning? We have some people in the room asking us to recommend a laser for them.
Indeed, I think I'm in with G that the bulk of the laser shock pinning is done with nanosecond lasers. And just as a general comment, if you have a material like plastic or stents or something where you want to have very precise machining of something you don't want to get hot, you want an ultrafast laser. If instead you want to cover large areas and apply a lot of heat to a more robust surface, typically there are much less expensive ways to do it. So that is not the area. But actually, now having gone online, there actually is a hit for laser shock pinning and femtosecond lasers. So never say never.
Thank you very much for that. We also have another question in the chat asking about what is the ideal laser for microfluidics manufacturing? Jim, can you comment on that? What is the ideal laser for manufacturing of microfluidics? I understand that they are talking about manufacturing in glass processing, and we're going to hear in a bit from femtoprint. But before we go to them, can you comment on this, Jim?
I don't know the answer. I think because of needing the precision and because of glass being one of the materials that does benefit from ultra short pulses, I can imagine either femtosecond or picosecond lasers will work. As Raul said, the cost of the machine is one of the problems. And of course, you're going to hear more about higher power from Jens at the end. Part of is speed. So I wouldn't be surprised if it's pico or femto, but I don't know enough about the details.
And we're indeed going to go to Jens in a bit. But before that, ladies and gentlemen, it is time to be serious because we're going to talk about serious business. This is the micro-optics revolution. We're going to hear this sentence a lot in the coming months. We have a supply chain that goes from the masters all the way to applications in lighting, in LiDAR, in silicon photonics, the strongest companies in manufacturing micro-optics. Today, we bring to the table one of them, all the way from Switzerland. We welcome first time at an Optica online industry meeting, femtoprint. Andrea Lovera, CTO of femtoprint. Thank you very much for being with us. We know each other for many years. It is great to have you in the room with us today. Tell us what you do and tell us how we can help you do it even better. The floor and the attention of everyone is yours.
Thank you very much, Jose, and hi, everyone. So in femtoprint, we are active in contract manufacturing of glass micro devices. And how do we do that? Well, we use femtosecond lasers. And thank you to G for the nice introduction on the use of femtosecond laser, because what we do is very similar and was already covered partially by her presentation. So here in this slide, I summarize a bit some of our areas of expertise, starting from the free-form manufacturing of glass. So we do that using a special process which is laser-based, but also require an etching step, also known as selective laser etching, which is used to structure glass in 3 dimensions. And that is really the core technology of femtoprint. However, thanks to the fact that today's femtosecond lasers are so versatile and there are so many parameters to exploit, we have in time developed other applications with different parameters. For example, fabrication of optical patterns and waveguides or marking in the volume, but also laser welding for glass to glass and glass to other materials. Other area of application are drilling. We are really focusing a lot of efforts in these days in making very precise holes like ferrules or fibers. We use lasers for dicing, surface treatment, and also for ablation of metals. Sometimes we produce components with electrodes, and we like to structure them in 3 dimensions with laser ablation. We develop our own machine, therefore we know we have a very specific need, and we know well how to use the femtosecond laser, but there are a lot of unmet needs, like some already mentioned, for example, beam shaping. We would love to be able to go from Gaussian to other type of beam shape without removing the parts. That's still an unmet need. And the fabrication we do is done either at single die level or at wafer scale. And here we see some example of wafers with holes up to 300 millimeter wafers. Now I'd like to show you some application of our technology, starting from freeform microdiffusers. So here you see a microscope picture of a diffuser, and there you see the 3D section. You really can appreciate the complexity of these lenses. In this area, we are able to produce components with very nice surface quality, below 20 nanometers. And we are constantly working in improving the shape accuracy. Today, we are typically below 2 micrometer for these complex shapes, but for other more traditional spherical, we can be more accurate than 1 micrometer. Another domain that I mentioned before is fabrication of waveguides. Waveguides is becoming a very hot topic because waveguides can be used for many different things. For example, to connect optical fiber and photonic integrated circuit. So here we fabricate waveguides in different materials, fused silica, Borflow, TIGO-XG, and a different wavelength ranging from the visible to the near IR. The waveguide can be single mode or multi-mode, can be coupled with ferrules, like you see in this image. These are ferrules. Then the waveguides are barely invisible. They look like tiny modification. Here we are increasing the refractive index really to guide the light from one point to another point. And they can also bend in both X, Y, and Z direction. Typical losses are below 0.7 dB per centimeter, which is fairly decent for application in micro optics and connector for PICs. One other very important element here is that we can fabricate the waveguides and the ferrules or other optical elements in one fabrication step. That means we don't have to remove the parts to do the 2 different processes. And that's a real advantage because we can have a very good positioning accuracy between the optical elements. And today, where the trend is to miniaturize everything and the core of the fiber are getting smaller and smaller, we are not really limited, or we are trying to get the best possible coupling between the elements in this way. And then, as mentioned, we are doing a lot of holes recently. This is an example of a big ferrule that hosts more than 2,000 fiber, is used for an astronomical purpose, courtesy of MIT. And here you see the ferrule in the center, where the diameter can be controlled below 0.5 micrometer on all the array. And then we can add fiducials, like here, crosses, other alignment features to be able to align precisely this component with, for example, an array of microlenses. Again, one of the strengths of our technology is the precision, but also we are able to manufacture these guys on very thick glass wafers. Our record is 32 millimeter. This is not 32, but it's already 2 millimeters. So people can get very straight fiber. You don't have to worry about tilt issue there because you have a lot of space to insert your fiber in. And finally, another very important USP for us is the combination of functionalities. And this microfluidic chip actually represent nice this statement. So here we have a microfluidic channel, and then we have ferrules that comes into the chip from the side. You see there are some chamfer for easy insertion of fiber. And then in the volume, we have cylindrical lenses. So this is used to monitor the liquid density going through the microfluidic channel and integrate fluidics and optics. Of course, this is not done as a monolithic piece because the channel is simply too long, but is produced using welding. And again, femtosecond laser. So we put two slides of glass together. One is machined, the other is not. So we can remove the material from the lenses here, which are buried, and then we can seal everything in an hermetic way. And this chip can be used in machine to do real analysis of liquid. So the combination of functionalities in microfluidic optics, but there are many other. We are not really only active in micro-optics, we are active in microfluidics, in watch industries, and in many other different markets. So, and with this, I would like to open the talk to the discussion. Thank you.
Thank you very much, Andrea, and congratulations on the success of FemtoPrint. I know you guys are growing, you guys are hiring, and you are really making a big difference on many different markets. So congratulations on what you're doing today. We are not here to find you customers, we are here to find you partners and suppliers. We have meetings to solve that. We have a lot of questions and comments from you, questions from Spectrogon, from Lumoscribe, but I'm going to go first to Spectrogon, all the way from Sweden. Optica corporate member specialized in the thin film deposition of optical filters. Spectrogon, thank you very much for being with us today. Please tell us what is on your mind.
Thanks, Jose. Yes. Well, we're mainly, I'm located here in New Jersey, so I'm on the US side. We are a manufacturer of optical components. Our specialty here would be for the holographic gratings, sinusoidal profile for pulse compression applications. And then we do specialize for thin film AR coatings, bandpass filters for sensors, lasers, instrumentation marketplace. So it was good to hear the new applications and just to see what is the future, Jose.
You have, I think, a question, comment, perhaps room for cooperation with FemtoPrint?
Well, if there was do you see a need for thin film bandpass or an edge filter type coatings in some of your applications?
So as mentioned, we develop our own machine, so we are constantly trying to improve the machine in many different ways, and optics is for sure one of the main things that we look for. We typically look for beam shaping, but in the future, who knows? We are also exploring different wavelengths now, so I will be happy to look what you do in more detail, for sure.
Oh, excellent. Thanks.
The next question comes all the way from Greece. Andreas from Lumoscribe. What's on your mind?
Hi, Andrea. It was very impressive presentation, very good results. I would like to ask you a question about the propagation loss of the waveguides. The 0.7 dB per centimeter is for which wavelength?
So the characterization was done in the near infrared, typically 1313 nanometer and 980. Those are the wavelength that we have studied more.
Okay, thank you. I mean, you didn't make any measurements in visible, or
in the visible, we have done something in the red, but today our focus is really near infrared.
Okay, okay, thank you.
The next question in the room comes from a company that requires no introductions. We all love it. Edmund Optics. Randall Hinton. What's on your mind? Randall? His microphone doesn't work, but he wrote the question for me. So, Andrea, what are the considerations for choosing the focus objective for these microprocessing applications? Will any of the shelf objective work?
They do. Of course, we look for objective with filters or coating that are compatible with the wavelength we use. It's typically 1030 nanometer or the harmonics. So they work, but we also like to correct aberrations and do some stuff. So sometimes we use special objectives, but also the off-shelf objective works.
And I saved the best for the last, because this discussion is going to be exciting. For all of you who are active in photon integration, pay attention to this, because Jean-Philippe has the question. Jean-Philippe, please voice what you have in mind.
Yeah, well, I was thinking, I saw these waveguide writing application up to now, and I know that it's possible to inscribe low-loss waveguide in glass, but I know that also that it's difficult to reach the same results in crystal. So have anyone succeeded in fabricated low-loss waveguide in silicon, for instance? Not for instance, in silicon. That's
before
very
we give the floor
specific.
to Andrea and to G, before we do that, Jean-Philippe, what is low loss? And let's say at 1550, what is low loss?
Yeah, well, I would something well below the dB per centimeter, I would say 0.5, 0.3 will be acceptable as low loss, but that's arbitrary. But that's what I meant. That's what I meant.
So we are not talking 0.1 dB per kilometer like silicon
No,
nitride.
no,
We are talking
not
about
such.
0.3, 0.5. Yes, I wanted to clarify that because it has happened in a similar meeting talking about silicon nitride and silicon photonics. Andrea Lovera, do you want to comment? Has anybody succeeded in the fabrication of low loss waveguides on silicon?
I'm not really familiar with silicon, but I'm familiar with some other crystal like lithium niobate. I was recently in a meeting for quantum, and they talked about waveguides in lithium niobates with decent performances. Yeah, but in silicon, I'm not aware.
What are the typical losses that you have on your 3D waveguides on glass that you write with the femtosecond laser, Andrea?
We are typically below 0.7 dB, sometimes below 0.5 dB per centimeter.
And what is the bending radius that you can achieve?
Minimum around 25 millimeter. Because the index contrast is not super high.
Even in the case of crystal, because sorry to interrupt, because usually what people do is write two lines of stressed, or that's stress induced waveguide, right? That's not the index that's changed. So you can still do relatively tight bend as low as 25 millimeter, even with these types of waveguides. Because
yeah, absolutely.
Yeah. Okay, good. That's great.
Jean-Philippe, there is a person in the room who really wants to answer your question. So I'm going to give her the floor. G from Rochester, please tell us what's on your mind. I know you really want to talk.
I just want to answer. Philip was asking the loss in crystal material. So we have written a waveguide inside indium YAG crystal. It's a laser material. We have achieved about 0.21 dB per centimeter.
0.21?
0.21, yes. In terms of silicon, silicon is a very narrowband material, and there are some investigation on writing waveguide in silicon. I think right now the loss is pretty high.
Yeah.
They're probably higher than what someone in the room. I don't know if someone in the room, whether someone in the room is working on writing in silicon.
No, that's difficult. That's what I was asking.
I want to give the floor now to a friend of us, a person who has been very active in helping me connecting companies. I'm going to go all the way to Canada to say hello to Alain Villeneuve. Today with Consultants Opta, every time I talk to you, have a different affiliation. Alain, please tell us what brought you to this meeting and what do you have in mind?
Well, thank you, Jose, for the introduction. I can talk about Consultants Opta a little bit. But I've been working on building and using ultrafast lasers for more than 30 years. I started a company building fiber laser and fiber deliverable picosecond tunable lasers. But right now I'm a consultant on laser and fiber lasers, their design and the applications. And I have one answer and one question to ask. Actually, I was looking to answer the question from Jean-Philippe about 2-micron, about writing waveguide in silicon.
Yeah.
And there's a gentleman called David Grosjean. He's in Aix-Marseille in France, and he has done some work on that. And if you write me, I can send you the reference. I was looking for the loss of the waveguides, but my computer crashed. So anyway, on the other computer. So contact me. If I find it, I'll put it in the chat after it. Oh, okay, now it's okay. Sorry, I don't have the answers, but they've been working on that. And it's not 2 lines like people were doing back in the 1990s. But anyway. Mm-hmm. But I have a question to the panel. We've been working a lot on talking a lot about the 1-micron lasers, but for silicon, for example,
yeah, it
would be better to use like 2-micron or even 3-micron. And recently, there's been a lot of papers on high harmonic generation and XUV generation with 2-micron. It's a little bit better, and there's also the application of 3-photon absorption or third harmonic generation for biophotonics imaging. So I was wondering, anybody working on 2-micron, thulium dope lasers? And the other question I have is, what is the biggest application for 2-micron laser?
Thank you very much, Alain. We got to the question. So I'm going to ask anyone in the room. 2-micrometer lasers, anybody working on 2-micrometer lasers, and what are the applications for 2-micrometer lasers? Who would like to comment?
Thank you.
We have 2 people who want to comment, or 1 person. All the way from Jena, capital of optics in Europe, Jens Limpert. Jens.
Yeah, actually, I'm fully convinced that 2-micron is the future and has several advantages compared to 1-micron. What are the applications? A few you have mentioned. What I can add are medical applications. Frequency conversion, you mentioned a few, 2 terahertz, X-ray, mid-IR works better with 2-micron laser as a driving or starting wavelengths, and silicon photonics, right? 2-micron ultrafast lasers at 2-micron can be used for waveguide inscription in silicon. So this is just a few where I believe 2-micron.
And which one is the biggest one, if I might say so?
Probably medical.
Probably medical.
Yeah.
Jean-Philippe, tell us what's in your mind.
Yes, so just to mention that I know guys working here in Quebec City that that produce 3-micron laser, and that thought they were mentioned at the beginning of the meeting. They are called femtom. So they were in the list. So if anybody is interested in their laser, they're doing 3-micron laser. So it's fiber laser. It's not femtosecond laser, but it's short pulse duration.
If they are hearing us, they are fantastic. And one of the key applications they have is thin film, but they also have key applications on interactive photonics. Great company indeed, Fenton. Thank you very much, Jean-Philippe. You know, Jean-Philippe, one of the cool things of this meeting is that some people come to the meeting with a challenge in mind. So I'm going to go to Erwin Verheest, who has a challenge for both Femtoprint and I think also the group from Rochester OG. Erwin, what is your challenge?
Well, the question is, I earlier mentioned photonic wire bonding, where you go from one waveguide to another waveguide. And Andrea, you mentioned that with your machine, you could do X, Y, and Z writing of your waveguide. So my question is, can your machine also do that relative from one waveguide to another waveguide?
So
locating the core and
if they are on the same substrate, yes. If they aren't, we can still do alignment. We have optical alignment in the machine, but in that case, we may be slightly less precise.
Okay. So you can actively locate the waveguide before you're writing your.
Yeah, so we have to add some marker that are inscribed in the same time as the waveguide, and then we use those fiducial to locate the waveguides.
Okay.
And the marker can be in the volume, of course.
Oh, I love answer this question.
I know.
So we have written waveguide in 2 different materials, monolithically, without needing additional alignment, all by femtosecond lasers. But I cannot tell you the details.
Oh, you can, but after you sign an NDA with Fix and you start a new cooperation. Thank you very much, G. In a meeting like this is the secret. It is not a webinar. We really want people to start working together. We really want people to make new friends on 2 hours of your time. We are on 1 hour and 40 minutes now, and we say the best to the last. We go to Jena, capital of optics in Europe, a place where they have infrared cameras from Genoptic detecting you are going to speed and you get a ticket in the tunnel to enter. I got one myself, and I go to Jens Limpert, to Fraunhofer IOF. Thank you very much for being with us. Please tell us, most important, how can we help you being greater than you already are? The floor is yours.
Yeah, many thanks for the kind introduction. Hello from Jena, Germany. So I would talk about the wish list of things end users would like to see from the lasers. This was at least a task given when we discussed for joining this meeting. To what I know, I'm aware of that all the use or most of the use of ultrafast lasers is connected to this effect of cold ablation, nicely explained by Jim Kafka earlier. So traditional applications and markets are connected to cold ablation, where the ultra short laser pulse modifies a certain spot, and the material what's left behind is not harmed that much. So ultrafast lasers are kind of matured, yeah. So what are key specs? You are totally aware of that is pulse energy, pulse duration, repetition rate with that average power, and so on. So all the long list. So this is the page 1 of the data sheet, and there are many vendors, and then are further other important features, and also addressed already by Jim Kafka. Important features such as size, initial cost of ownership, uptime, reliability, worldwide service network, and so on. And to the best of my knowledge, most of the applications related to cold ablations are totally happy with the, let's say, 100 watt class of femtosecond lasers, or even below. This is the power they can handle, and at a power where this reputation of cold ablation is alive. And many vendors in the meantime, and a few have been mentioned earlier here in this meeting, offer 100 watt class femtosecond, picosecond laser, including the process know-how. And as a matter of fact, there's a strong competition on the market, and the prices go down. Actually, customers have the choice, and the important features such as uptime, service, size, and cost of ownership, these parameters decide who gets the contract and who not. So, and as a matter of fact, the technology is even more advanced. We have most recently we have realized a 10 kilowatt femtosecond laser, and there are even companies offering kilowatt class femtosecond laser systems. But to be honest, most applications related to material processing, whatever is the material, a metal or a tissue, a glass, most of these applications struggle with these extreme average powers. The cold ablation is valid for a single femtosecond laser pulse. At a kilowatt average power, we cannot talk about cold ablation. So it's certainly a challenge that, or if these kilowatt ultrafast lasers, and they do exist and become available and more reliable day by day, whether they can open up new big markets with this scaled power. So, and on the other hand, there are end user needs related to very specific parameters. I can share a story that we typically specify our lasers with 0.1% pulse-to-pulse stability. What is a very good value? And most recently, we got a request for 0.01% pulse-to-pulse stability. This is for a highly nonlinear process, and we had to develop the entire characterization system to be able to characterize and to improve our lasers to 0.01% pulse-to-pulse stability. This is just an example for a very individual need, and there are many of them, and all of them are niche markets. And Jose, you asked for the question today, what are the new killer applications for ultrafast lasers? And to be honest, I didn't hear a good answer so far. Maybe you can define what you see as a killer application, and maybe we can discuss this afterwards. So ultrafast lasers are quite advanced, and I have the feeling that the applications start to struggle with the performance lasers can deliver. And on top of that, we witness a huge gap what lasers can do today, and where maybe really new markets are popping up. And these are applications maybe related to laser-driven particle accelerations, electrons, positrons, ions, and so on, protons. And even the ignition of nuclear fusion is discussed in the laser community. And these applications, they need parameters which are orders of magnitude above the state of the art. So they need joule class or even kilojoule of pulse energy, femtosecond pulses, not 300, not 150 femtoseconds. They need 30 femtoseconds or even few cycle pulses at high repetition rates, 1 kilohertz, 10 kilohertz. So 10 joule, 10 kilohertz is 100 kilowatt of average power. So these are end user needs they define today, and I believe this is a huge R&D effort, a task for the entire community. In between, we believe that new wavelengths can indeed open up new application fields, and with that new markets. And this was already discussed. So primary sources, 800 nanometer, 1 micron, typically the emission wavelength. Secondary sources are frequency converted to what you see here, the entire electromagnetic spectrum from terahertz, mid-IR, XUV, and even X-rays are generated by lasers and generating in these spectral regions coherent or incoherent ultra-fast light. It's coherent laser-like light. And the statements here at the bottom, end users might need to think out of the box. Maybe their process where they use today a 1 micron or 800 nanometer laser might even work better at other wavelengths. Maybe a 2 micron or 3 micron femtosecond laser does the job better. And what I can tell you, the statement here, ultrafast laser technology is that versatile and rich in possibilities. And I think the end users have simply to use these new possibilities. And with these statements, I stop my presentation and would like to answer your questions.
Thank you very much. First of all, I love when people ask me things. I just tell you my opinion. If you ask me what is the killer application for ultrafast for femtosecond lasers, I would say it's twofold, and we're preparing meetings on that. The first one is to bring femtosecond laser to production of electronics, microelectronics, and semiconductor. And we're going to have a specific meeting to target that and to see how we're going to do from memory repair to dicing. But the second one, which I think is one that we want to address in a separate meeting, we are seeing a huge market opening on frequency comms. For those of you who work with me at ECOC, they saw how companies like Menir Photonics have been taking very close to the need for free space optical communication. And there we are still looking at what is the way to reduce the price, the size, and increase the manufacturability of ultrafast laser for those frequency comms at 12.5 gigahertz. For me, those are the two markets which will maybe not address today, but I'm preparing separate meetings with specific end users for addressing those two markets. Jens, but this is my opinion. My opinion is worth nothing because I work for an association. I want to talk to the people in the room to see how they can help you. And on that, I want to give the floor to a person who didn't interview yet, and I didn't intervene yet, and is a very important person for Optica and for me in particular. I want to give the floor to David Hagan from Thor Labs. David, good afternoon. Good afternoon here. Good morning, I think maybe where you are. David Hagan from Thor Labs. 1, 2, 3, 1, 2, 3. David Hagan from Thor Labs cannot switch on the microphone. This happens when you make the meeting live. It's okay. It doesn't matter because it will be coming back to you. One thing that I would like to ask you, Jens, there is a big program on laser-based manufacturing with many Fraunhofer centers. And I have been in touch with many of the Fraunhofer. There's an umbrella, there's a cooperation. I don't want to talk about politics, I want to talk about opportunities. What are the main challenges that you will see that these companies here in the room could cover? Could you highlight one or two challenges that we think we should work on to help one of these big programs to provide ultrafast laser manufacturing from Green Deal all the way to automotive?
Yeah, there are some challenges. I mean, you probably refer to the CAPS, the Center of Advanced Photon Sources. We developed there this kilowatt, 10 kilowatt ultra-fast lasers, and the optics technology is that advanced that we are able to handle this power. Yeah, we even can design the beam delivery, but at the end, the applications are not able to handle these power levels. So what some Fraunhofer institutes develop are kind of beam splitter, diffractive optical elements, basically at the end, distributing this entire power to many spots, to patterns, to keep the throughput and the cold ablation alive, even at this high average power. So this is really the main challenge to my perspective, or to my opinion, is that the application can keep up with the speed of the laser source development. This is my impression. That's the main challenge. And the laser is there, or the lasers, at different wavelengths in the meantime, at kilowatt and beyond average power, very high pulse energies. We know how to bring this to the application, but what are the applications which are able to handle these kind of powers? And here we are opened up to application labs, one in Aachen, one in Jena, where customers come with their applications and their samples to our lasers and try whether they can work with these enormous power levels and see some benefits.
The beam delivery is the biggest challenge by a mile. And providing the people with affordable ways to bring this specialty fiber that can support high power and can be suitable to this ultrafast laser is a challenge. Is there a way that Fraunhofer IOF and some of the network Fraunhofer can support the challenge of beam delivery to the companies in Optica? Jens.
Indeed, there are in this consortium, there are Fraunhofer institutes developing special beam delivery optics and systems, actually, and scanners and so on to handle these power levels. And please contact me, and I can share the numbers of these institutes and contact persons. I think there are solutions for kilowatt class beam delivery from the laser to the applications. It's not fiber delivery, I have to say.
For those of you who watched the meeting from the beginning, I promised G from Rochester that I would find you the fiber, right? This is the person that you need to contact. Jens Limpert, he will put you in touch with the right people at Fraunhofer who can supply the fiber that you are needing for the beam delivery of your ultrafast lasers. And if they can't, at least you will make extremely good business connections. Jens, there is a question for you coming all the way from Vilnius, Lithuania. Konstantinas Acho, what's on your mind?
Yeah, more is not a question, it's also a comment. I know some, there's very nice femtosecond applications like surface structuring that we have seen made on glass, but also for industry, let's say, plain wings would benefit from it. So I think, multi-kilowatt femtosecond lasers could go to, big industries. Just the key is to have constant performance. And I think that this high energy systems are still high power, high energy systems are still working all in lab environments. So that's the key.
Well, that's one of the keys. Another key application, Jens and Konstantina, for ultrafast lasers is the quantum technologies, which is beautiful because it's a hype. There is money there, and people who, like me, who love quantum, they can find the edge of technology. One of the cool things working at Optica, I work with some of the best in the world in quantum. My friend and partner in crime, Carl Williams, is in the room. Carl and I have been working on putting the strongest agenda in a quantum workshop, which I remember on the 8th and 9th of November in Paris. Carl, what are the applications of ultrafast lasers in quantum tech?
Well, they're mostly novel applications at the moment. I mean, the ion trap people have used them for cleaning their surfaces of that trap because stuff gets on those traps and cause noises which degrade the quality of their gates and other things. They've been used, they're used again in ion trap computing for ionizing the ions that get captured by the trap. Typically, those are ultra fast. They've also been used to do very fast gates in both atom and ion trap quantum computing, mostly from an experimental expertise. I mean, part of the problem is as you try to miniaturize things, you need very high quality optics, and putting the ultrafast lasers in there create problems, but that doesn't mean that in the future this won't be done. They've been used some in creating entangled photon sources through parametric down conversion of certain types of crystals. So they have some applications. I don't think they have become mainstream, but maybe just because it's early years, it's always interesting to see where technology goes.
Carl and I have been having the time of our lives because we've been talking to quantum companies, and we asked them on the 8th and 9th of November to come to Paris, to IXBlue, and to share what they need from the optics supply chain. So these are the companies who are going to come to Paris on the 8th and 9th and tell us how the people from the optics, from the ultrafast laser, from the interactive photonics can help them. It has been a really amazing adventure talking to all these people and ask and understand what they need from us. I think I can talk now to my friend David Hagan from Thor Labs. David, are you with us? Yes, here he is. Loud and clear.
Perfect. Yeah, sorry about that. So I was a bit slow on the uptake. I just wanted to go back in time about 15 minutes to when somebody was asking about 2-micron femtosecond lasers. So yeah, just scanning the website because it's constantly evolving. Thor Labs does offer actually a 2-micron femtosecond laser in the kilowatts. Yeah, there's more details there, but I believe there was also another question about 2-micron applications and silicon photonics specifically. So I just wanted to very quickly mention that data communications is also a niche application area there on silicon platform because of the stronger free carrier effect and also lower propagation loss. So yeah, that and hello everybody.
Thank you very much, David, for being with us. And David Hagan is one of my entry points of Thor Labs. You're looking for a cooperation with one of the key companies in our network. This is the entry point. I will be happy to introduce you. There's a question, anonymous question. I don't like that, but I'm going to allow it. Anonymous question for Andrea Lovera, coming from an anonymous asking person who wonders, he's just curious. He's working on a biophotonic phosphate glass. Are you able to manufacture micro optics on phosphate glass?
I would say we have never tried. We have tried with a few like Eagle G, for example, or Borofloat, but not on those type of glass.
You know what I did try? I did try to bring an online industry meeting and had the experience of connecting everyone in 2 hours of the time. Together with Tom Hausken and Elise Fritz-Gage, we did our best for making sure that you connect. You want to get in touch with any of the participants today, all you have to do is send us an email and we'll make sure that you get introduced. It has been 2 hours of your time, which we talk about the end user application from Fraunhofer IOF, a summary of MKS, the micro-optic manufacturing with femtosecond laser from FemtoPrint, the services on Femto and Pico from Microrayeus, and he talked to us about automotive lighting. And we even talked about the 3D waveguides from Rochester, and G found a very good room for cooperation. I would like to say it has been a blast. We started on time, we finished on time. Thank you very much for being part of this new adventure. Thank you for being part of a global industry network.